Okay, all right. Well, happy Wednesday, happy second week. We're just kind of moving right along. Hopefully homework 1 is going okay. I see a lot of good discussion and questions on Campus Wire, which is always encouraging. And so thank you to all of you who are posting your questions. Thank you to everybody who's responding. And again, just want to encourage you to upvote one another's answers. It doesn't cost you anything to do so. It helps out, the people who respond. So do that. And yeah, if you haven't been checking Campus Wire, you should. I think there's a lot of helpful information. Always also just want to encourage you to use the search. I think most of you guys are doing that. Haven't seen too many repeated questions, but that's it. You know what? Actually, I forgot to check if this link still works. Let me just check. I think it still does. And yes, great. Okay, so this is a textbook. I think there's some problems kind of related to this, and so you can click this link. That will take you to the website, and if you do it while connected to the UCLA network, you can just download it. If you live in a off-campus apartment or something, somewhere not on campus, then you'll have to connect via the VPN, okay? And also Hadley Wickham's advanced R book on control flow. So this is kind of how we have our code do different things depending on different conditions, okay? And so as far as programs and code go, a major thing is to execute this code under these conditions and different code under different conditions, okay? And the way we check to see if a condition applies or not is with logical values. So basically, if this thing is true, then do this. And if it's not, if it's false, then you do something else. That's how we control how our the flow of execution goes. Okay, so we call this flow control. All right, and so in R we have logical vectors, true and false, sometimes NA, and these are our logical operators. These are the different operations that can be done with true or false values. And these operators will coerce things into logical values. So you have the or, x or y. You have the ampersand, x and y. You have the not operator, exclamation point. And you also have exclusive or, XOR. And if x or y is not illogical, like if it's some kind of number, a 0, it'll get coerced, right? 0 gets coerced to false. Anything else, all other numeric values get coerced to true, with the exception of n. Well, I guess NA is not really a numeric value. It's an NA. That remains NA. Okay, all of these are also vectorized. They'll do element-wise comparisons, as well as recycling. And vectorized operators will return, vectorized operations will return a vector of logical values. Okay. We also have these non-vectorized logical operators. You have the non-vectorized or, the double or, and then the non-vectorized and, the double and. These non-vector versions only work with length 1 logical vectors, okay? Length 1 logical vectors. If x has a length greater than 1, it's going to return an error, okay? If y has a length greater than 1 and y is evaluated, it's going to return an error, okay? If y has a length greater than 1, but it's not evaluated, R will not error. There's no error going to happen. And I'll talk about what it means for y not to be evaluated, okay? This, older versions of R, that is prior to 4.3, so the behavior of the non-vectorized or and changed, I would say, maybe just a few months ago, okay? And so check your version of R. If you have an older version of R, you should update, okay? If you have an older, so like when you start up RStudio, it will tell you right at the top, I think, what version of R you have. And so here I'm starting up R. Okay, so here mine, I have 4.3.2. That was, I guess, updated October 31. Okay. All right, so here is vector versus non-vector. So X is a vector true, true, false, false. Y is false, true, true. And so when you do or is true, true or false is going to return true, true or true will be true, and only false or false returns false. So true, true, false is true, true, true is true, false, false is false, and false, true is true. Okay. X and Y, both things have to be true in order for it to be true. So true and false is false, true and true is true, false and false is false, false and true is false. Okay. Here I've got X non-vector or Y, and because X has a length greater than 1, this leads to an error. It says length equals 4 in coercion to logical 1. Okay. Here I have a false and Y. Okay. Now Y has a length of 4, so you'd expect this to return an error, but it doesn't. Why not? Because whenever you have a false and blank, you don't actually need to know what the blank is. Okay, false and whatever is always going to be false. So when R sees this, it says, well, I don't even need to figure out what Y is. So this instantly evaluates to false. Y isn't even looked at, so there's no error. Okay. Similarly, true or blank is always going to yield true. It doesn't matter what Y is. And so Y isn't evaluated. Even though Y is length greater than 1, there's no error here. So true or Y, or true double or, true non-vector or Y, just evaluates to true. However, if I do false double and, or false double or, the false non-vector Y, here now we have to actually see, is Y true or is Y false? And then Y gets evaluated. R looks at this and says, oh wait, Y has a length of 4, and so therefore we get an error there. Okay, length 4 in coercion. Logical. Okay. What about NA? What happens when we do NA? What happens with true or NA? What is that going to produce? That's going to produce true. Okay, we actually don't even care, right? True or whatever is just going to be true. Okay, true and NA. What's that going to produce? That's an NA, because we need to know what this missing value is for us to be able to give you an answer, right? False or NA, that's NA. False and NA, false and NA will always be false, okay? We don't actually need to know, right? So exactly as we said, true or NA is true. True and NA is NA. False or NA is NA, but false and NA is false. Okay, exclusive or is true only if one of those things is true and one is false. So you need to have one true, one false. So here I've got X and Y. So true, false is true, true, true is false, false, false is false, false, true is true. And then if anything is NA, NA and true is NA, NA and false is NA, and NA and NA is NA. If I said that all correctly. All right, you have any and all. Any is the generalization of or to more than 2 values. All is the generalization of and for more than 2 values. So here I've got true, true, true. Any of you, that's true. All of you is true. Okay, true, true, false. Any for V is true. True, true, false are all. That becomes false. And then false, false, false. Any is false and all is false. So these are kind of our non-vector versions of this. Here's a question. If we add a zero-length vector, such as logical 0 or null, to a vector of logical values V, that should not affect the result of any or all. Okay, right? So if you have a vector of true, true, false, true, or whatever it is, okay, and then we were to add a null value or a logical 0 into that thing, basically we end up with the exact same thing as we did before, and our answer shouldn't change, right? So that is, any logical zero along with v should produce the same as any v, and all logical zero with v should produce the same results as all v. Okay, so with that in mind, what does any logical zero return? Okay, yeah, any on a length 0 vector is going to return false. Okay, that is to see, all right, so here I have u, v, and w, and we can see that these will all produce the same results, right? True, true, true. Any on u is going to produce true, and then if I combine the logical zero with that, that will still remain true. Okay, true, true, false, any of that will remain true, and things like that. False, false, false. Any on w returns false, and then any combined on x combined with w also returns false. If any on the logical zero returned, say, true, then this response would be different. Okay, and then kind of using the same kind of logic here, all on a length 0 logical vector returns true. Okay, because if all on a length 0 logical vector returns something other than true, that would affect how this statement is evaluated. Right, so all on u, which is true, 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 currently evaluates to true. If all on x combined with u returned, if all applied to x were anything other than true, this response would be different. Okay, the any and the all on v and all on xv, or all on w and all on xw, all return the same. Okay, we have comparison operators, so this we can use to kind of compare generally numeric values, but I guess you can also use it to compare string values, and these will produce logical values. They're vectorized, they perform recycling, and so you can do stuff like is some 3 equal to 3, or 3 not equal to something, 3 greater than something, less than something, things, so on and so forth. Okay. You have one thing to keep in mind is that if you can do comparisons with strings. A lot of times we'll use like equality, like is the character string A equal to the character string A. That makes sense, but you can also do comparisons, and this is kind of like, is one thing alphabetized before the other? A weird side effect is that 1, 0 gets alphabetized before 2, right? And you might have noted, like, this might happen on like your computer when you name files, and they get sorted. Sometimes like a number 10 gets sorted before 2, or things like that. Of course, the number 10 is not less than 2, but when in strings or character form, 1, 0 in quotes is less than character string 2. Okay. There's also like what happens to the symbols, and just so you are aware, the ASCII symbols are arranged in this order. This, I don't know if there's any kind of rhyme or reason. I think this is just from the ASCII table. All right, we got a bunch of is functions as well. These will return true or false logical values depending on whether the object is this thing. So, right, is something NA, is something null, is something logical, is something numeric, etc., etc. We have that. Okay. All right. Conditional statements. We have if statements, and we use that. And depending on if the condition is true or false, something is going to happen, right? So conditional execution of blocks is achieved via if statements. So the condition in an if statement, as far as the if condition, must be a length 1 logical vector, and it cannot be NA, right? Conditions of length greater than 1 result in an error. Older versions of R didn't error. You'd get a warning, but now if you put in a condition of length greater than 1, you get an error. If you put something in that's not logical, it will try to get coerced into logical. If the condition is NA, you get an error. Missing value where true false is needed. Okay. So if you see this error, missing value where true false is needed, that means you have an if statement, and whatever's in that condition in the if statement produces an NA. Okay. If you get if the condition is length 0, you get an error. Argument is of length 0. Okay. And then curly braces are used to kind of group the expressions that will run when the conditional if statement is true. If there's only one line to execute, then the curly brace is optional, but I recommend always using the curly brace. All right, so I have x is a vector 1, 3, and I can say 1% in percent x, and you can say is one of the values in x, and that's true. And I could say if 1 is in x, print hello. Well, this statement is true, so therefore this code right here, this line, print hello, what's going on? Print hello gets executed. All right, and so hello gets printed. All right, let me give you your first view quiz answer. So the letter E. E as in elephant. E. All right, here I have x is 1 and 3. I have x less than or equal to 2. This produces a logical vector of length 2, right? So now if I do if x is less than or equal to 2, I get an error, right? And it says the condition has length greater than 1. Error and if this thing. So this, again, error messages are helpful. It tells you like where the problem is and what's going on. It says the condition's length greater than 1. So it's saying this part right here that's producing an error. Okay. If you do have a logical vector length greater than 1 and you want to use it inside a condition, then you got to kind of like wrap it in an any or all statement, right? So are any of the values in x greater than or equal to 2? That's true, right? 1 is false, but 3 is true, greater than 2. So are any of the values greater than 2, greater than or equal to 2? That's true. So here I can say if any x greater than or equal to 2, then do that, and so that gets a value. Okay. If you have an NA, you get an error, right? So here, if x, the fifth element in x, this is out of bounds. Single square brackets on out of bounds produces NA. So if this is, if this missing value is greater than or equal to 2, we get an error. It says missing value or true false needed. Okay. This is a very common error that you'll run into. Missing value where true false is needed. Okay. And what that means is you got to go through your code, see why this thing is producing NA value. This often happens inside a loop. You got like for I and 1 through 100 or something like that. And then you have some kind of vector like x, but it only has a length of 50. And then so when it gets to I equal to 51, and you have something like x, the 51st value in x, that's going to produce an NA, and then your conditional statement is going to be NA, and then you run into this problem. Okay, very common error, but also fairly easy to troubleshoot. Okay, here, if you get a length 0 logical vector or integer vector or something like this. So here I can, x is 1 through 3, and I say, hey, what is the index where x is equal to 4? Okay, and there's no value in x that's equal to 4. So I get a length 0 integer vector. And so if I do something like this, hey, is the I don't know what's happening to my Adobe here. Okay, so basically I'm asking, hey, is the fourth value in x, right? Or is the value in the index of the value that has the value 4, is that equal to 4, right? Is the fourth value in x equal to this? Well, this is not going to work, right? Here I've got an integer 0. Is that equal to 4? Well, that's going to produce a length 0 logical vector, and I get an error here. Argument is a length 0. Okay, so those are all kinds of the different errors that you might encounter with an if statement. let's talk about nesting our conditional statements. And so this is where we have if, and else, right? And so so far we've seen if this is true, then do this. Then we have if it's not true, we can test another condition. So we have else if, and if this other condition is true, then do this. Otherwise, do this, right? So here I'm going to say if x is less than 0, print out negative. If that's not true, check to see if x is greater than 0. And if that's the case, then we'll write positive. And if this is also not true, then that must mean x is 0. And so in our case, I say x gets the value 3, and this is false, so it checks this condition. This is true, so it prints out positive, okay? And then this part in the else statement here, the code chunks associated with kind of the if that was false and stuff, these don't even get evaluated. All right, here I've got x is 0, so again, this is false, and so this must be true. This gets executed, and so it comes out and says it's 0. Okay, here's some poorly written code. And here I wrote, if x is greater than 0, print positive, okay? And then I have an else if x greater than 1, print bigger than 1. Otherwise, print not positive. This code chunk will never get executed, right? Because there's never going to be a time where this is false, but this is true, okay? The only way this statement right here, print bigger than 1, will get executed, that only gets executed if this statement is false, but this if statement is true. And there's no, on the real number line, there's no value that satisfies this being false, but this being true. So this line would never get executed. Right? It's important to note that if is not vectorized, but sometimes you want to have some kind of vectorized operation, and so we have if-else. If-else is vectorized, and I've got an example of this coming up later on. Okay, so if always requires a logical vector of length 1, but sometimes you have like a whole bunch of things, and so if that's the case, you can do something like an if-else. So here I've got if x is equal to 5, then we'll store n as what yes, otherwise n is no. This can be reduced to if-else x equal 5, the condition, and this is going to be the result when the condition is true. This is the result when the condition is false. Okay. And in this statement, x can be a vector of values, and you'll get kind of vectorized output. I've got an example coming up. All right, but before that, let's talk about loops. And I guess I'll go ahead and give you your second view quiz answer, which is the letter C. C as in cat. C as in cat. Okay? And I recognize all of you have already been working with if statements and loops and all of that, because to do your homework, you have to know this. And so this has all been covered in Stats 20. I don't know if you got into the nitty-gritty regarding like the all of the length 0 stuff with the ifs. Maybe yes? Okay, well great. Then it's this is review. All right, so kind of probably the most common loop we have in R is the for loop. And you have kind of this for x in some kind of vector. And what it will do is R is going to go through the vector and evaluate this code for each value in that vector. So here I'm going to just say cat x squared separated out by and then a space, and so this just kind of outputs 1 through 10 squared. Okay. The for loop can iterate through any vector. So here I have a list, and I've got list with a length 3. First thing is a vector 1, 2, 3. Next is a vector a, b, c, d, f, g, and last is another vector true, false. And so here I could say for y in L, for y in this list, so each element of y is going to be basically the element inside each train car, and I could say print out the length of y. So it's going to say, okay, the first element in that first train car has a length of 3, the element in the second train car has a length of 7, element in the third train car has a length of 2. All right, so we can iterate over other vectors. You know, we're probably accustomed to seeing, you know, for x in 1 through 10, but again, it doesn't have to be an integer vector. It could be any kind of vector here. Here's just another example here. I've got the first 5 state names in alphabetical order. Okay, so if you load up library data sets, there's a vector called state.name, and that's going to have, you know, the 50 states in alphabetical order. And so we could just go through this vector, and we could say for state in state name 1 through 5, okay, the first 5 states, we'll just cat state has number of characters in that element, and then we'll say letters in its name. So Alabama has 7, California has 10 letters in its name, so on and so forth. Okay. As far as storing the results of your loops, it's almost always better to create an object where you're going to store your results first, rather than growing the object as you go along. Okay, but of course you can only do this if you know how many values to expect. So here I'm going to say I'm expecting 10 to the 7th. So what's that? 10 million values. My results is going to be this big vector, length 10 to the 7. And here I'm going to say store in this for x and sequence along results. So basically x in 1 through 10 million, do x squared and store that in results position x. And that takes my computer 0.64 seconds to do that. Okay. Here, this thing is slightly slower, but here it didn't require that I know how many values I'm going to have in my results. So I just have results. I just put in 0, and then I do the kind of the same thing for x in 1 through 10 million. The results is going to be x squared. Okay, results position x. And that takes a few more time, a little bit more time, 2.83 seconds. This is system.time measures how long it takes to execute this line of code. And then this is kind of the worst way to do it. Here I had to do 1 through 10 to the 5, so only 100,000, basically 1% of the work, 1/100th of the work. But it was so slow that if I tried to do anything longer, it like brought my computer to a halt. So this is, here I start off with an empty vector. Results is just an empty vector, and then I'm going to grow this by kind of copying basically results along with kind of the new value of x squared. And then, so this kind of grows the vector by copying all of the all of the previous results, tacks on a new thing, and stores it back into results. And so this took 13.6 seconds just to do 1 through 10 to the 5. And my computer would have dragged on if I said, do it for 1 million or 10 million values. Okay, so that's for loops. We also have while loops. While loops keep running until a condition, while a condition is true, and then when that condition becomes false, it stops. Okay, and so this is especially helpful if you don't know how long a loop needs to run, right? So if you have some kind of iterative process and you have some kind of stopping criterion, right? There's some kind of convergence that you're looking for. You just have to let it run until you reach that criterion. Okay, so here's a question. We start off with I equal to 1. The results are going to go from, we're going to have a length of 10, and I've got NAs right now on results. And I'm going to say, while I is less than or equal to 10, what I want to do is I want to do I squared and store that into results position I. After we do that, we will increment I. We're going to do I plus 1 is I. And then it iterates, right? Okay, so when this is done, we have results as 1, 4, 9, 16, 25, 84, 100. And the question is, what is the value of I when this code has finished? If I go and I ask R, what is the value of I? I is what, 10, 11? What do you think? Yeah. I has the value of 11, right? Because at I equal to 10, when I equals 10, I less than or equal to 10, this evaluates to true. And so results position 10, we're going to put in 10 squared, and we get 100. And then I gets the value 11. We increment I to 11, and then it reaches the end of the code block. So it goes back to the start of the loop, and I has the value of 11. 11 less than or equal to 10 is false. So now that this evaluates to false, it kicks out of the loop. So I takes on the value 11. Okay. Repeat is kind of like while true, right? So you can do something like while true, and that would run forever, right? So this is kind of sometimes you get stuck in this infinite loop because the condition is always true. And repeat is kind of like that. Repeat is like while true, and that was going to run forever until it encounters a piece of code that says break, right? So here, this is pretty much the same code chunk. I start off with I equal to 1, right? And then we're going to just repeat this code chunk until we encounter break. So we say put into results position I squared. After you do that, increment I by 1, and then we'll check this condition. If I is greater than 10, then break. Break is going to quit out the loop. So again, when we do this, we get I equal to 100, and the value of I after the loop is done is 11, because at I equal to 10 and results position 10, we put in 100, but then we increment I to I plus 1, so I is 11, and now if I is greater than 10, that's now true. We break out and we quit the loop. Okay, so we've seen break. Break just ends the loop, but we also have a statement called next. Okay, so next is going to just end the current iteration and immediately move on to the next iteration. Okay, so it's it's kind of like, listening to music on a playlist. When you hit next, you don't listen to the rest of the song. Okay, it just moves on to the next track. And similarly, in a loop, if it encounters next, it just moves on to the next iteration. Okay, whereas break is just kind of like stop. Okay, it just stops the loop entirely. Okay, so here, what is this going to output? I say for I in 1 through 10. If I %2, so if I mod 2 is equal to 0, if I is even, basically, then break. And then, but if you don't do that, then the base code in the chunk is just cat I. Output I to the screen, basically. All right, so what are we going to get? Well, it starts off with I is 1. When I is 1, this is false, so break does not get evaluated, so it cats 1 to the screen. And then it goes to the next iteration, I is 2. When I is 2, this is true, and then it breaks. And so that's the end of the code. So it's just going to output 1 to the screen. Ta-da, that's the end. Okay? If I run the exact same code chunk, but I replace the word break with next, what is this going to output? So with 1, this is false, so next is not evaluated, and it goes down, keeps running, and it outputs 1 to the screen. Okay, this reaches the end, so then it goes back to the top. I is now 2. With 2, this code chunk, this statement is true, so it evaluates next. It skips this part, and it goes to the next iteration, 3. Okay, at 3, this is false. Next is not evaluated, so it cats 3 to the screen. Then it goes to the next one. 4, this is true. It evaluates next, and it skips it. So we just get the odd numbers output to the screen, 1, 3, 5, 7, 9. Okay. We have sequence length and sequence along. So a lot of times we want to use some kind of loop that indexes, across some kind of object, not necessarily the elements of the object themselves. And in order to kind of assist with this, there's a few handy functions. We got sequence, sequence along, sequence length. So here, again, I have this list. L, it is a list of length 3 with different elements inside. And so the results, I want length 3 in the results here, length of L. Okay, and I can say for x in sequence along L. Sequence along L is going to produce a vector 1, 2, 3. And then inside the results, I want to say in position 1, store, give me the length of the object inside L double square bracket x, right? So double square bracket x is going to pull out that first element, and we ask what is the length of that, and it's going to give us 3. So we had similar code here, but here I'm using sequence along here because I want to kind of store, in position 1, position 2, position 3, and things like that. Okay, so this is fine. So I got sequence along. And these are all kind of very similar. So if you did 1 colon length L, length of L is 3. So 1 colon 3 is going to produce 1, 2, 3. You could do sequence along L, and that's going to produce 1, 2, 3. And you can also do sequence length of 3 or sequence length of L, and you get 1, 2, 3. So it feels like, okay, well, these all produce similar results. Why do we want to use sequence along versus, say, 1 colon length L? What's the edge case that kind of breaks everything? So sequence along is the recommended, okay? Sequence along is the recommended, and that is because sometimes you get a 0 length vector, and if you just use 1 colon length of L, that's going to kind of break your code, okay? So, it's very simple, 1 through 10, 1 through whatever, and you might say like, okay, let's just take our vector v and just do length of v and 1 colon length of v, okay? Well, here I've got a vector L, which is a 0 length list. I just write, it's an empty list. And if I do 1 colon length L, then I get this vector 1, 0. And if I run some kind of loop here, so if I do 4x and 1 length L, okay, and I do give me the length here, then I get basically a subscript out of bounds. We're asking for L double square bracket 1. This doesn't exist, so I get subscript out of bounds, or something else could go wrong, right? So we do that. Okay. On the other hand, if I do sequence along L, okay, rather than getting this vector 1, 0, I just get a 0 length integer vector, integer 0. So 0 length integer vector. And so if I do for x and sequence along L, well, nothing gets executed. This is not going to attempt to do anything because for x in basically this 0 length vector, we get, it's just going to not execute anything, all right? Similarly, if you do sequence length, length of L, all right? So length of L is 0, sequence length 0 is going to give you a 0 length integer vector as well, okay? So both of these methods using sequence along or sequence length is going to be safe for 0 length objects, which is what we recommend. Okay, let me give you your last view quiz answer. Last view quiz answer is the letter D, D as in dog, D as in dog. Okay, a lot of times we want to vectorize our code. So in R, one thing about R is that it's pretty, in my opinion, it's fairly easy to start writing code in R. Okay, you don't have to worry about types. You don't have to declare these little buckets to store your values and stuff like that. If you took like C++ or Java, you have to like declare these kind of buckets where you're going to store values, and you don't have to do that in R, right? You got a lot of kinds of things, but R doesn't kind of compile stuff. It just interprets the thing, and so what that means is when you have loops, it's slow, okay? R is slow when you do loops. And so a lot of times we want to vectorize our code, meaning we just kind of evaluate an entire vector and we avoid having a for loop, okay? That's not to say loops are bad, okay? But if you have like a loop inside a loop inside a loop or something, that's generally going to run very slowly, Okay, and so if you can kind of vectorize your operations, that's great. Okay, now that said, not always possible to vectorize. It's not always worth the effort. Okay, and but if you can improve things. There's kind of this quote that says premature optimization is the root of all evil. And, that's hyperbole and a joke. But if you try to optimize too early, like the steps are get everything working and then optimize. If you try to optimize before you even get things working, you're going to ask for heartache here. All right, so here's a function, okay? So here's a piecewise function, mathematical function. We've seen stuff like this, right? For x less than or equal to 0, we want to evaluate it here. For x between 0 and 1, use x squared. And for x greater than 1, use the square root of x, okay? Now, with an if statement, we can do this, right? We can say f is a function of x. If x is less than or equal to 0, then the value is going to be negative x to the third power. Else if x is less than or equal to 1, because this is, I don't need to check if x is greater than 0 because it's only going to evaluate this if this is true, right? So if x is greater than 0, then this is false, and then I'll check this. If x is less than or equal to 1, then the value is x squared, and then otherwise, my value is the square root of x. And then once we have done that, return the value. All right, so this is our function, and this works, okay? However, if I try to do this on a vector of values, so if I say x is a sequence from -2 to 2, sequence by 0.01, okay? This doesn't work, right? Because as soon as I plug this in, it says the condition has length greater than 1, right? So it's going to put in the sequence, this entire vector here, and it's going to say, oh, wait, that's got a condition length greater than 1. So here, this fails, plot values fails, okay? Okay, actually, I didn't evaluate this. This is incorrect here, this text here. But we get an error because it's not vectorized. So what we have to do is we have to kind of run a loop, right? So we're going to say x is the sequence. My plot values is going to be currently kind of an empty vector, or a vector of zeros. And then, so I say for I in sequence along x, what I want it to do is take the ith element of x, evaluate f on that, store that into plot values I, and then now that I've done that, I can plot x along with the plot values, and I get the function. Okay, negative x cubed from here to here, x squared from here to here, and then square root of x for x greater than 1. Okay, so this evaluates correctly. This is what I want. Okay, that's a non-vectorized version. What we can do is we can vectorize the function using if-else. So here I'm going to create a function f2. This is going to be if-else, and I'm going to say if-else, if x is less than or equal to 0, then what I want it to calculate is negative x cubed. Okay? And if that's not true, then what I want it to evaluate is another if-else. Do an if-else, or x is less than or equal to 1, and if that's true, return x squared, and if that's not true, return the square root of x. Okay? So I have kind of this nested if-else. If x is less than 0, x less than or equal to 0, then do this. Okay? If that's not true, okay, then check this thing. Okay? We do an if-else, and we do that, right? And so with kind of like this comments removed and the spacing thing, it's very compact. So I have this function f2. I've got if else x less than or equal to 0, negative x cubed, evaluate if else this, and do that. And this is vectorized. I can now just produce x is the sequence from -2 to 2. I can do plot values, f2, function 2 on x. I get this warning, nan's produced. Okay, but then I can plot this, x versus plot values. Okay, so this is vectorized. I didn't have to run a loop where I'm going to say, hey, for each element in this vector going from -2 to +2, do this. Okay, I just said, hey, run this out, and it does. Okay, why am I getting nans produced? What is going on here? Warning and square root x, nans produced. When is square root of x undefined? For negative values, okay? So what's going on? The reason why, okay, because you're like, why would I ever get square root? When am I taking the square root of negative values? Because when you look at this, it only evaluates the square root of x for when x is greater than 1, okay? But the way if-else works is it takes your input vector, in our case going from -2 to +2, and it evaluates the entire vector, the true values for the entire vector, and then it takes the false expression, in our case, square root of x or whatever, and it also evaluates it for the entire vector. So it takes all of the true, so the way if-else works, if I go back a bunch of slides here, okay, it says the condition to test, the result of the condition is true, and the result of the condition is false. So it evaluates the result when the condition is true for everything in x. It also evaluates the result for everything in x when the condition is false, and then it just uses the results of this thing, the condition, to decide, do I take A or B? Okay, and it just kind of mixes and matches these to kind of produce your result. So it evaluates the entire vector is what it's doing. So over here, it's evaluating the entire thing, even for the negative values. It's evaluating square root of x even for the negative values, and it's just when it produces the output, it just kind of mixes and matches all of these things without worrying about it. Okay, so that's why you get this nans produced. All right, so it evaluates the entire true expression, evaluates the entire false expression. Okay. Okay, we have a couple more operations that are very kind of quick and fast for matrices: row sums and column sums. These are, if you remember these, this can speed up your code. So you probably learned about like the apply family of functions. Apply is great, but if you're just going to do something like apply a sum to an entire matrix, then row sums and column sums are even faster than apply. Okay, so here I have this huge matrix. Okay, 100 million values here, 100 columns, and I could just kind of say, hey, for sequence along, calculate the mean of each of these things, and it takes me 3.67 seconds. Okay, here I did apply along margin 1, calculate the mean here, and that takes me 6.48 seconds. Okay, but here if I just did, hey, do the row sums and divide by the number of columns, that takes me 0.27 seconds. Okay, so this is much faster than apply, and even kind of faster than this kind of for loop where we evaluate the entire matrix and stuff like that. Okay, again, if you don't remember this, that's okay. These other methods work, and the time, 6 seconds is a lot longer than 0.27 seconds, but in the grand scheme of life, it's also not very long either. So you can sit around. A lot of you asked me, like, are we going to get evaluated like if my code is not super efficient? Right now, the answer is it's fine if your code is not super efficient. Obviously, we should strive towards making things more efficient. But right now, if you can get it working, you should just feel proud of yourself, okay? And so if you get it working, great, turn it in, and you'll get full credit. As far as the homework things go, you're only responsible for just kind of making sure all of the meeting the requirements described in the homework, and then basically we evaluate primarily looking at the test cases in the homework. So if your code passes all of those test cases, then you'll probably get full credit there. Okay, but yeah, obviously, if you can make your code more efficient, that's great. But you also have other classes going on and things like that. So how much time can you dedicate towards making your code more efficient? I guess that's up to you. Obviously, if you have the time and expense and energy to do it, then great. But yeah, are you going to lose points if it's not super efficient? The answer there is no. Okay, we'll go ahead and end here for today. Have a great rest of your day. We'll see you on Friday.